Hello and welcome to section 3.3, derivatives of trig functions. We start with the sine function, okay, and we look at the sine function. We want to look at the curve for the sine function, and just a reminder that when we do sine of x, we're talking about the angle whose radian measure is x. So looking at the graph for the sine function, okay, the sine curve is the one up above us, and we want to look at the derivative of that sine function. And if we map out the derivative function to it, okay, notice everywhere there's a horizontal tangent line, we map it to 0 on our derivative function. Okay, and this derivative function actually looks very close to the cosine curve. Okay, and the reason for that is because it is. Okay, so our first derivative is the derivative of the sine is equal to the cosine. Okay, so it's important to remember that fact. Okay, so let's do an example. So here we have y equals x squared times sine of x, and we're going to differentiate. Okay, so we'll use the product rule. Okay, so this tells us that it's going to be the first function times the derivative of the second function. Okay, so derivative of sine would be cosine of x plus second function times the derivative of the first function. Derivative of x squared is 2x. Okay, and just clean it up, okay, without the parentheses. So we would have x squared cosine x plus, and we can move the 2x in front, 2x times sine of x. Okay, now derivative of the cosine is equal to negative the sine function. Okay, so it's important to make note of that. Okay, so that's our second derivative. Okay, derivative of cosine is equal to negative the sine of x. Okay, let's take a look at the derivative of tangent of x. Okay, so in order to do the derivative of tangent of x, let's show that derivative by rewriting tangent of x as the sine of x over cosine of x. Okay, and so by doing so, now we could take and use the quotient rule for derivatives to show what the derivative of tangent would be. Okay, so now taking the derivative of sine x over cosine x using the quotient rule, this would give us the denominator times the derivative of the numerator, and the derivative of sine is cosine x, minus sine of x times the derivative of the denominator. Okay, derivative of cosine is negative sine all over the denominator squared. Okay, so cosine of x squared. Okay, so let's simplify things a little bit. Here we have cosine times cosine, that's going to give us cosine squared x. Here we have negative sine times negative sine, that's a positive. Sine times sine would be sine squared x. All over cosine of x squared is cosine squared x. Okay, next we have cosine squared plus sine squared, or otherwise known as sine squared plus cosine squared. Well, we know this as an identity. right? Sine squared x plus cosine squared x equals 1. Okay, so that gives us 1 for the numerator over cosine squared x. Okay, so basically we have 1 over cosine x times 1 over cosine x, which is secant times secant, so this equals secant squared x. Okay, so we could say that the derivative of tangent of x is equal to secant squared x. Okay, and so here are our 6 derivatives for the trig functions. Okay, and you'll see their counterparts here with cosecant, secant, and cotangent. Okay, so put these to memory. They do come in handy when you're doing problems involving these types of derivatives. Okay, so the more you know, the better off you'll be. Okay, let's take a look at an example. Differentiate the function secant x over 1 plus tangent x. For what values of x does the graph of f have a horizontal tangent? Okay, so let's first do our derivative. So this will be a quotient rule. So we have denominator times the derivative of the numerator. Okay, now the derivative of secant is secant x tangent x. Minus secant x times the derivative of 1 plus tangent x. Now the derivative of 1 is 0. Derivative of tangent is secant squared x. All over the denominator, 1 plus tangent x squared. So what we could do next is factor out a secant x from our numerator. So we'll have secant x, and then we'll have 1 plus tan x times tangent minus secant squared x. Okay, distribute the tangent into our parentheses. So we have secant x, tan x plus tangent squared x minus secant squared x over 1 plus tangent x squared. Now we see elements of another identity here. We have a tangent squared x and a secant squared x. The identity that involves those are tangent squared x plus 1 equals secant squared x. So now if we rewrite this as tangent squared minus secant squared, I would subtract secant squared and I would have tangent squared x minus secant squared x, and then minus the 1 to bring that to the other side. Okay, so this would get replaced with negative 1. Okay, so I have secant x times tangent x minus 1 all over 1 plus tangent x quantity squared. Okay, so this will be the derivative function for it. Now we want to remember, it says for what values of x does the graph of f have a horizontal tangent? Okay, so for it to have a horizontal tangent, we have to see where the derivative equals 0. Right, so horizontal tangent is where the derivative, or f prime of x. So for this to equal 0, the only way that's going to happen is if the numerator equals 0. Right, we'll have a 0 over something else. Okay, now secant, okay, one property of secant is never 0. Okay, you could look at the graph for secant and verify that. Okay, secant x never equals 0. So it all depends on tan x minus 1. Okay, so tangent of x minus 1, take that factor, set it equal to 0. So we're looking for all the places where tangent is equal to 1. Okay, so think of all the angles where tangent is equal to 1. Okay, so angles like 45, 225, etc. Right, every pi after 45 is going to equal tangent will equal 1. Right, at pi over 4, and then every pi after that we would get at 225. Okay, so 5 pi over 4, we would get tangent of 1, and then just keep going around every pi. Okay, so we could say in general x would equal pi over 4 plus n times pi, where n is an integer. Okay, and that would generalize it for all solutions. Okay, analyzing the motion of a spring. An object at the end of a vertical string is stretched 4 centimeters beyond its rest position and released at time equals 0. Okay, so here's our figure. Okay, note that downward direction is positive. Its position at time t is, okay, so here's the position function. S equals, it's a function in terms of t, 4 times cosine t. Find the velocity and acceleration at time t and use them to analyze the motion of the object. So let's take a look. We have S equals 4 cosine t. To get the velocity, we would take the derivative of our position. So derivative of 4 cosine t would be 4 times, derivative of cosine is negative sine. Okay, so therefore this will be negative 4 sine t. And then the acceleration would be, take the derivative of the velocity. So negative 4 times derivative of sine would be cosine. So negative 4 cosine t. So let's take a look at all three graphs, which I've placed here. So the one in pink, that's our position function. The one in the blue is our velocity function, and the one in green is our acceleration function. Okay, the object will oscillate from negative 4 to 4. Okay, so we go 2, and then these will be 4, and then this will be negative 4. So object will go between 4 and negative 4. The period is going to be 2 pi. Okay, period is 2 pi, just like for cosine, the period is 2 pi. Speed, remember speed is the absolute value of the velocity. Okay, so if we look at the velocity function, we had negative 4 sine t, so take the absolute value. So that gives us 4 sine t. So that means if we have sine of t to be equal to 1, then that'll give us the maximum. Right, when sine of t is equal to 1, right, when sine is pi over 2, let's say, that would give us our maximum velocity. Okay, notice here the maximum speed, and then same thing replicates when we get here at 3 pi over 2. Okay, and then the acceleration, okay, is 0 when we talk about position being 0. And it has its greatest magnitude at the high and low points. Okay, so lowest be down here, highest be here. Okay, so that would be looking at the graph of those functions, the graphs of those functions. Let's take a look at our next problem. Example 4, find the higher order derivative from a pattern. Find the 27th derivative of cosine x. Okay, so we have f of x equal to cosine x. If we do f prime of x, then we get negative sine x. If we do the second derivative of negative sine would be negative cosine of x. Derivative of negative cosine, that would be negative of negative sine. So that's going to be positive sine x. And then the fourth derivative of x, derivative of sine would be cosine. Okay, if we do fifth derivative of cosine is negative sine. Okay, so we're back to, we got this pattern going on. Okay, it appears every fourth derivative we're going to get to the same the same result. Okay, it's going to be some kind of cycle of 4. So now we know that every fourth derivative is going to be a cosine. Right, so we're going to go up to where, the 27th. Okay, so that means f of 4, 8, 12, 16, 20, 24th. The 24th derivative would be another cosine. Okay, so the 25th would be negative sine. 26th would be negative cosine. And the 27th would be a sine x. Okay, so that's how we would do that problem, just looking at the pattern of repetition between the derivatives. Okay, any questions, just let me know, email me, or bring it up in class. Have a good day, have a good night. We'll see you soon.